Hello, my name is Bing Li. I'm a PhD student for the Reliability and Risk Engineering Laboratory at ETH Zurich. My research interests include the risk analysis of cascading failure in power systems, electricity markets, and the interdependency of energy networks. Today, I'm presenting our research on estimating the impact of the electricity market on the risk of cascading failures in power systems. This work is done in collaboration with my supervisor, Professor Giovanni Sansavini. The introduction of electricity markets unbundled the power generation from the transmission network, which may push the operating conditions closer to the security limits. There are two main concerns. First, there is high uncertainty due to market volatility. And second, the selection of generation sources is mainly price-oriented. It is important to answer the question of how the diverse market-based dispatch can affect the risk of cascading outages in the system. We investigated both of the representative market structures, the centralized and the decentralized market model. The dispatch plan selected by the power market is tested with the cascading failure analysis to quantify the losses that a cascading event can lead to. In a decentralized market model, the market is cleared independent of the transmission network. We developed an optimization for the bidding strategy and the safe scheduling of the generation company. We modeled an iterative function for matching the supply and demand. And we manage the line congestion with a security constraint optimization. In the centralized model, the generation price reflects the marginal cost. The dispatch is generated with one optimization, which minimizes the generation cost while subject to the security constraints. In the cascading failure analysis, random contingencies can be introduced to the system. Overloaded lines are identified and disconnected. In case of a topology change, a function is used to detect the island condition. In each island, the safety interventions are modeled to restore the power balance. If the cascade stops, the severity of the consequences is measured as the load shedding. Otherwise, the simulation will continue. We validated the cascading failure analysis model against the historical blackout data on the reduced WECC network. The model is able to capture the blackout size for 99% of the events. Also, the probability distribution is consistent between the results and the data for up to 6 line outages. As we expected, in diverse operating conditions, the centralized and decentralized dispatches are affecting risk of load shedding in different ways. Here we clearly see that in high load conditions, the centralized dispatch is associated with lower risks of load shedding in the power system. Now we look at the case when generation capacity in the system increases. On the contrary, we found that the centralized dispatch can lead to more severe consequences with a larger probability. In this market model, the units with low marginal price have dispatch priority. Since these units are denser in certain areas, the distribution of generation sources in the systems become geographically inhomogeneous. Islands with significant generation deficiency can be formed when the system is split into islands. In this paper, we contributed to the blackout risk assessment by modeling the two representative power market structures and the development of a cascading failure analysis. The results show how the interplay between the physical infrastructure and the market structures can impact the risk of cascading outages. The decentralized dispatch can lead to higher risks of load shedding in heavy load conditions, while the centralized dispatch is associated with more risks of load shedding if the generation capacity increases. Thank you for your attention, and I'm looking forward to meeting with you in San Diego.